The Black-Scholes model revolutionized finance by providing the first closed-form solution for pricing European options, developed by Fisher Black, Myron Scholes, and Robert Merton. Let's look at the formula itself. For a European call option, the price equals the spot price times N of D1 minus the discounted strike times N of D2, where S0 is the current stock price, K is the strike, T is time to maturity, R is the risk-free rate, sigma is volatility, and N represents the cumulative normal distribution. The terms D1 and D2 are standardized measures that capture how far in the money the option is, adjusted for time and volatility. These N terms have powerful probabilistic interpretations. N represents the cumulative standard normal distribution, the area under the bell curve. N of D2 represents the risk-neutral probability that the option expires in the money, the probability that the stock price exceeds the strike at expiration. N of D1 is the option's delta, the hedge ratio. It tells us how many shares we need to hold to replicate the option's payoff. Important distinction. These are risk-neutral probabilities used for pricing, not real-world probabilities of profit. Black-Scholes assumes stock prices follow geometric Brownian motion. This stochastic differential equation says the stock's return has two components: a deterministic drift and a random shock driven by a Wiener process. Starting from today's price of $100, we can simulate many possible future paths. Notice how the paths fan out over time. That's the effect of compounding uncertainty. The key insight is that we can price an option by averaging its payoff across all possible paths, and Black-Scholes gives us that average in closed form. Now let's see the formula in action. We'll use a strike of 100 half a year to expiry, 5% interest and 25% volatility. This dashed line shows the intrinsic value, the payoff if the option expired immediately. It's zero below the strike and rises linearly above it. The Black-Scholes price is always above the intrinsic value. That difference is what we're paying for. As the stock price rises, watch the call value climb, and when the stock falls, the option loses value. But notice it can never go below zero. The gap between these curves is the time value, the premium we pay for the possibility that the stock could move further in our favor before expiration. Let's summarize what we've learned. First, Black-Scholes provides a closed-form solution for European options. No simulations required. Second, it uses the risk-neutral valuation framework, where we discount expected payoffs at the risk-free rate. Third, option value equals intrinsic value plus time value. The formula captures both. Fourth, the model assumes constant volatility throughout the option's life. In practice, volatility isn't constant, which is why practitioners use extensions like SABR, local volatility, and Heston models.